So I'd like to welcome you all here for the inaugural lecture of Professor Dan Toal, Chair of Electrical Engineering and Robotics. And for those of you that don't know me, there's probably half and half here. I am Tom New, I'm the interim head of ECE, and I'm your MC for the night. So before we start, some housekeeping. This is being streamed live, okay, so it will be recorded. So I hope that's okay with everyone. Please turn off all your phones or put them on silent if you can. And if a fire alarm occurs, God forbid, 2 exits at the back, 8 sides. Make your way outside. Now, I'd like to welcome Dan, his wife Jane, daughters Lily here behind me, and Rebecca and son Cullen here in front. His extended family members, his friends and colleagues, and today for his inaugural lecture. I think it's funny calling it Dan's inaugural lecture, but not you. This is a proud occasion for Dan and his family, and indeed it is the first one that my partner ECE has actually had. So I've known Dan for my entire career in UL, over 30 years, and during this time I can say that his academic and his research career, I think, is held up as an example to us all. He's a leader in robotics research in the University in Ireland, where he founded and grew the only marine robotics research centre in the country. He led the development of our robotics and electrical engineering programs in the ECE department, and he's been a core academic in the department and our flagship electronic and computer engineering program for as long as I can remember. Dan has been an advocate for his team, and he has quite a substantial team, a lot of which are here tonight, for as long as I know him. He's been loyal to them, he's fought their corner when necessary, and I think we all admire him for it, even though maybe at times we were the one who was fighting it. I now hand you over to our Vice President of Research and Innovation, Professor Kevin Ryan, who will say a few words on Dan's career.
Okay, thanks very much. So, first of all, it's my immense pleasure to introduce Professor Dan Toal. This is a fantastic occasion for his family, his friends, his colleagues. So Dan has been a distinguished member of our academic community. He's a leading figure in the fields of electrical engineering, robotics and marine technology. As the Chair of Electrical Engineering and Robotics in the Department of Electronic and Computer Engineering at the University of Limerick, and he's the founder and director of the Centre of Robotics and Intelligent Systems, which is called CRES. And in this, Dan has made remarkable contributions to both academia and industry. So a little bit of your background, Dan, if you don't mind. Kind of like this is your life, a bit of that. Professor Toal's journey in engineering began with an honours diploma in electrical engineering from the Dublin Institute of Technology. This was followed by a BSc in engineering from Trinity College Dublin in 1984. He furthered his expertise with an MSc in manufacturing systems engineering abroad, which is in Cranfield University in the UK, in 1986, and he later earned a PhD in marine robotics from us here in UL in 2004. And by the way, Cranfield is probably one of the best universities in the world in the area of materials engineering. She moved from one of the best universities to another of the best universities. So we're very grateful for that, Dan. His professional career includes extensive experience in the electrical power and high voltage sector, with GEC in Britain from 1985 to 1988. Since joining the University of Limerick in 1988, Professor Toal has been dedicated to teaching and mentoring students in courses such as automation, robotics, instrumentation, avionics, sensors, and electrical machines. Professor Toal's research has been instrumental in advancing the field of underwater robotics. And in 2000, as I mentioned, the opening, Professor Toal founded the centre, the CRES Centre. So he's brought in a lot of very extensive funding, and I think one of the best days we had, and I think I was at that, was the launch of your art Rob down in the docks. And Dan and his team had engineered the robot to break a bottle of champagne off the Rob, which was very, very impressive. Under his leadership, CRES has become a hub for technological innovation and a key player in national and international collaborations. The Centre's work has positioned Ireland as a significant contributor to the global underwater robotics field by attracting top talent and securing substantial funding. And there's more to come in this space. And I was supposed to say on that as well, Dan's group and team have brought in substantial funding, European funding, so they're the go-to group in Europe when you're looking at marine robotics, and that's not an easy thing to achieve from an academic level. One of Dan's notable achievements is leading development of Tetra and Natus, the first autonomous underwater vehicles and remotely operated vehicles built in Ireland. These advanced vehicles are designed for deep sea exploration and mapping significantly enhancing our research capabilities and establishing UL Chris as a leader in marine technology. Professor Toal holds several patents that reflect his innovative approach to engineering. These include patents related to wind farms and seafloor topography, which are closely linked to his research in renewable offshore energy. His work in this area has contributed to advancements in sustainable energy solutions, demonstrating his commitment to addressing global challenges. As a mentor and supervisor, Professor Toal has guided 21 PhD students and established a summer internship program for undergraduates at UL, and many of those PhD students I think are here today to celebrate Dan. His leadership has fostered a collaborative and inclusive environment within the CRIS team, promoting a culture of equality, diversity and inclusion. Establishing strong collaborations with leading institutions and industry partners has been the core of Dan's work, resulting in joint research initiatives and advancements in marine robotic technologies, offshore wind and renewable energy. His role as principal investigator in several industry-led projects with SFI research centres of excellence, including MARI, LERO, and previously at Confirm, highlights his ability to bridge the gap between industry and academia. So I have another page to go, so I'll try. It's longer than I thought. Beyond his research and teaching, Professor Toal has made significant contributions to policy advisory and public engagement. He is a member of the IEA Task Force for Airborne Wind Energy and the French Oceanographic Fleet Scientific Advisory Board, providing valuable input to policymakers on international topics. His involvement in public events and lectures such as CFest and Point of Science underscores his commitment to promoting STEM education and engaging with the broader community. Professor Toal's ability to secure research funding is exemplary. As principal investigator, he has secured over 15 million in funding for more than 30 research projects since 2000. His leadership is also evident as the General Chair for the Oceans 2023 Limerick Conference and Exposition, a globally renowned event that attracted over 700 researchers and industry stakeholders to discuss the latest advancements in ocean knowledge. And that's no small achievement. I would say there's only a handful of conferences of that size would be hosted in Ireland. So to bring that to UL was an enormous achievement. Personally, I've been very fortunate to collaborate with Dan as part of the MARI Centre and a number of research projects. Actually, my involvement in MARI is because of Dan. So as we went into the second phase of the centre, Dan was looking to grow UL activities. So he reached out to me, and it's been very important for my research area, but also for UL. And we had some great meetings and great events after that, and I really enjoyed it. And he's also, I've always admired his passion for his research area and his drive to ensure the CRIS Centre and the University of Limerick are front and centre in energy research. And I suppose when you're talking about that nationally, this is often competitive as well as collaborative landscape. And Dan is exactly who you want to have in your corner if you're trying to secure the best outcome for your university. So he's always been a stalwart for UL. His commitment to his research team as a leader and mentor are exemplary, and the regard that he's held by current and former team members is a testament to this. To conclude, Professor Dan Toal's extensive contributions to electrical engineering, robotics and marine technology, along with his dedication to his education, mentorship and public engagement, make him a truly remarkable figure in our academic community. So please join me in welcoming Professor Dan Toal as he delivers his inaugural lecture.
If you can just turn that on. Okay, thank you, Kevin. Thank you, Tom. Thank you, Ken. Thank you all for coming. I'm delighted to be here. I'm visually impaired, so I've said hello to a number of you that I may know for 20 years without even recognizing who you are. So I ended up recognizing some of you 5 minutes after I was initiated talking to you. It's a bit odd, but I'm trying to get used to that. I wear these so people can see that I'm visually impaired, but then I end up taking them off because the tiny vision I have, they make it darker and dimmer. So anyway, so Lily is going to help me a little bit because technical hitches I've had. I'm going to have an audio cue telling me what side it's up because I can't see the slides. The trouble is the audio cue, when I advance the slides, the audio cue doesn't advance with it, so Lily helps me do that. So we'll start on the first slide, which I hope
First slide, yeah.
which I hope is up.
Okay.
So I've already said, it's telling me to say hello. I won't tell you everything it tells me. And I've also explained my visual impairments. The logo, that logo we've had since, I think, 1988. That logo sort of exemplifies what we see at our research world, and I don't think most people get it. I thought it'd be obvious, but I think it is obvious enough. Bring the world, it's used engineering and technical technology and science to bring us back towards the green planet, not the other way around. So let's not improve our enterprise and wealth at the cost of the planet. And so that logo, that's the meaning of the logo. The bit in the middle is electronic amplifiers with alpha to omega. So in most science and engineering, we run out of A to Z, so we end up using alpha and omega, and then we start using all sorts of other squiggles. And the symbol above is supposed to be a mechanical governor, and the symbol below is an egg timer. So it's just to give you an idea of using control and engineering technology in the systems research we do, but it's also with an imperative of doing it sustainably. So next slide.
Okay, we're awake, go back one.
Oh, slide 2.
Now we're good.
Okay. So now I have to listen to my cues. Oh, Fado. Jaws pronounced it Fado. Doesn't quite speak Irish. I'm not great at Irish, but anyway. So born in Dublin, my mum and dad and is Bob and Maureen. My father's family are from Dublin for a couple of generations. My granny is from County Down, and actually my great-grandfather, his family is also County Down. So the roots are County Down on the one side, and then my mum is from Leitrim. So like most Dubs, we're only a generation or two away from small farming, so most of us are really cultures. Lots of brothers and sisters. We're a big family, so there's a picture of my parents when the oldest was a baby. Then lots of brothers and sisters ever since, 9 of us in total. I'm the piggy in the middle, so 2 older brothers, 2 younger brothers, 2 older sisters, 2 younger sisters. And I won't introduce all of them by name, but you'll meet some of them, or you may have met them down below. And then my own family, Jane, my wife, Lily, Becky and Cullen are all here, and thank you very much for the support, everybody. Next.
Spacebar for next.
Next. Sorry.
Oh, don't go back.
Sorry.
So.
We did try coordinate this earlier, but now we're...
It's pressure.
Yeah.
Okay, we're good to go.
So the reason I'm talking about the stomping ground, because to some extent it set the scene for the research area. So we grew up not far from the coast in Monkstown, Dunleary, near the coast, near the piers. The countryside, it was suburban, but with lots and lots of green space. So as kids, we tumbled around the, in gallivanting and trespassing in other people's big estate lands, climbing trees, playing conkers, chasing, whatever the hell, all of that lot. So next slide. Yep. I'd say this one is maybe my school. So primary school was in Oliver Plunkett in Monkstown Farm. I think that's changed over time. There was 53 in my class, and we had 2 classes in the boys. The other was 50 as well, and there was also 2 classes in the girls. So it gives you an idea of the size of schools and the size of the population. Obviously, I'm one of the baby boomers. And then secondary, we went up the hill on the 46A bus to Stillorgan, which was an engineering and science sort of focused school with laboratory equipment. I think that's enough on the schools. Next up.
Okay.
So early spark ventures. When did I start getting interested in things electrical? So as a kid, it was already, Mars had a train set, that's the oldest brother. He may be online, but it's very, very early in Sydney. I remember when the Bakelite plugs and sockets used to break, being the one who was interested in that sort of thing. So fixing those. I do also remember taking apart, a battery and being discussing with the sticky goo that was inside it. But then one thing, asking the dad, the questions kids always ask their parents, which would win, a lion or a tiger, or why did the Tweety birds not fall off the electric wires electrocuted? And so at that age I understood they're isolated, they're not in touch with the ground, they won't get electrocuted. So climbing this dummy tree, if that's what's in the picture, the dummy tree was called the dummy tree because there used to be a wall beside it, so it was very easy to climb. So climbing up the dummy tree, on one bough, you'd come up nearly passing distribution cables. To test my theory that birds don't fall, I touched that. I could feel the buzz, but I didn't get electrocuted. But now, I can say that as a professor of electrical engineering, absolutely not a good thing to do. And I learned that in later education. Next up.
Okay.
So where are we up?
Can you hear now?
Slide. Okay, I think I've already sort of covered some of this. We used to be up and down to the seaside. Some of those early years and in the early 80s, the weather was a bit like today, so we were up and down to the beach nearly all summer long and through the rest of the year, down to Sea Point, spring diving, swimming, and then later on boating. So at one stage we repaired an old rotten boat, and actually where we got the boat was down in Boatyard in a boat club. It was a rotten, disbanded boat. We never found the owner. We repaired it and used it, but always located in the same location in case the owner sort of said, "What are you doing with my boat?" It was still in the same boatyard. Anyway, I'd say that's enough on the Galahad. So next up is college. Went to Kevin Street in DIT in Kevin Street, did electrical engineering, and with Kevin Street you end up getting the Trinity degree as well. So at the time Trinity didn't have so much engineering, so Trinity used to award degrees for the engineers in Bolton Street on the civil and building side and Kevin Street on the electrical side. So next slide.
Okay.
So then, after the degree, I went to applying for work while I was in London, but working in VEC distribution switchgear in Manchester. So worked as a high voltage engineer in high voltage test, working on distribution switchgear and working on voltage. I forgot the right presentation. The notes are a little bit different to what I expect, but anyway. Is this full of photos, Lily? It is.
This has the vacuum breaker on the side.
Okay.
Yeah.
So distribution switchgear was the product sold to all sorts of industrial, commercial and distribution electrical networks. Vacuum breaker technology was the core technology. So trying to open a switch at 6.6 kV all the way up to 66 kV. In the older technology, you'd have to have the switches contacts come very far apart so that you'd withstand the voltage of the 66 kV voltage, because as they were drawing apart, you'd draw an arc, and the arc would ionize the gas, and the gas would mean it was very difficult to switch. So they used to use oil breakers, where the oil would drag the arc over a whole load of insulator fingers, but then the vacuum technology with very high vacuum, down to 10 to the minus 4 torr, which is 10 to the minus 4 millimeters of mercury. When you even get a tiny opening, the vacuum will extinguish at the next current zero. So that was the core technology. So we'll go on for next slide.
Okay.
Next up. One thing I noticed, electrical engineers, the rate of change in electrical engineering was slower than I was maybe keen on when I was a young buck, in that, and part of the reason is electrical technology is designed to last. So the installation in the London Underground, the installation of Ardna Crusher in Ireland, these electrical plants, they're still in existence. They have a 100-year plus lifespan. So the influence that has on electrical engineering design is we don't want the service teams and the designers to be designing a new version like Microsoft Windows every year, because the service people have to service equipment for 100 years. So it means the technology is very well engineered, but it means the rate of change can be slow. And as a young buck, I thought, gee, I want a little bit more excitement than that, although there was the high voltage risk aspect. Next up.
Okay.
So I went and did a master's in GEC and was sponsored by in Cranfield, sponsored by GEC to do a wiring automation so that we could automate some of the manufacturing process back in GEC, and also did a large project with JCB, the digger manufacturer. Worked in the area of group technology, manufacturing systems, redesign, and computer integrated manufacturing. Next up, better get to the research fairly soon.
Sorry. Here we go.
Oh, yeah, forgot this. While in Manchester, I used to play in a small three-piece band. We called ourselves Choir Crack, which everybody in Ireland knows what that means, but most other people in most other countries wonder what's it. The new band that's into the new drug at the time from America. But no, we all know what it means. So we used to play clubs and the odd wedding and pubs and the like. Next up.
Okay.
So then it was back to UL after Manchester. So here since '88, came as a funded PhD student, but on week one was asked by my boss's boss, that was Ian McQuaid at the time, Dan, I see from your CV you've done robotics and sim and whatever. We're stuck for somebody to teach that next week. So I ended up in the first year as a postgrad teaching, I think, 5 modules. So the research slowed down or didn't happen at all, and actually the research took all the way to 2004 till I completed my PhD. I was working in robotics and manufacturing automation, and maybe some of the people online here, with Colin Flanagan was one of my eventual PhD supervisor. From the very beginning, I had Munir Ahmed and I had Peter Smith, who's maybe online from the UK, working in the factory automation area. But once I got the research group going and the technology focusing on robotics in the marine, but then I pulled the PhD in that direction and finished by 2004. But we had already got the group well funded by that stage. Next up then, I hope we're going to focus more on the research. The one thing, as Tom has already said, so my area of teaching is in electrical engineering and robotics, and so I have been involved in starting both electrical engineering bachelor's and master's programs and robotics bachelor's and master's programs. The robotics, we started way back in 2000, well, not way back, but back in 2006, but it was fused back into the general engineering entry in 2015. I don't remember exactly the year, but now it's just kept as an option, but now it's something similar is back on our books called mechatronic engineering, which is a program run between the electronic department and the School of Engineering, the mechanical engineering side. So it still uses all the same modules. And then the electrical engineering, we have something like 60 students per year coming in at the moment. So our demand is going to grow, and that is obvious now with renewable energy. Next up.
Okay.
Oh yeah, so the motivation for all things marine and the marine exploration. So you'll all recognize that photo, and I say most of us will have seen that film and know the music that comes to mind straight away. Next up. So imagine yourself standing on the prow of such a vessel, look up, you can see the heavens, you can see out to the extent of the heavens, and they even describe it that you see way back in time to near close after the Big Bang. And maybe you need a telescope help you do that, but look down, you can hardly see a meter through the water. So the underwater world is hidden, and that's what we need robotics to help us access it. So next up.
Okay.
Oh, so here's an image which was captured long after they discovered the Titanic on the North Atlantic seabed, and after that movie. I think this image was generated in the late noughties or around 2010. I don't know exactly, but it shows the wreck of the Titanic imaged with sonar, and the second picture shows, if you remember from the movie, the Titanic, when just before it sank, stood up after the vessel broke off and fell away separately. The forward part of the vessel went down like a torpedo, and so the two of them ended up sort of a kilometre or more apart. So that's the image we're seeing. The other robot beneath that is that tragic story that I think happened in the last couple of years, where this submersible was used and designed to go to that 4,000 meter, nearly 4,000 meter depth of the Titanic and bring people down. At an oceans conference in Seattle, I was in that submersible, but we didn't dive. It was in the harbour during the conference. So it gives you an indication of some of the challenges in the submarine environment. The pressure at the depth of the Titanic, you get 1 atmosphere every 10 meters. When you're down to nearly 4,000 meters, the pressure amounts to something equivalent to 1 ton per the size of your fingernail. So every fingernail size on that carbon fibre vessel's surface was bearing 1 ton pressure. Just gives you an indication of the, because it's air filled. So most of our robots, we go next. Most of our robots, we don't need a big air-filled compartment for humans. We can shrink down small air enclosures for some of the electronics that we can't have in fluid, but a lot of the stuff we can actually have in fluid. So we avoid that in robotics. So while Challenger Deep, the deepest part of the ocean, which slide am I on? The one with
Hidden Ocean.
the drain North Atlantic. Challenger, the deep part of the ocean is in the Pacific, not the Atlantic, but it's 11,000 meters deep. The abyssal plains are down at 6,000 meters. So while there are robots that have gone, or little science submersibles have gone to the bottom of even Challenger Deep, the trouble is they're so heavy with the wall structure, the scientists can get down, look how tiny portholes, see the outside environment, but they're almost immobile. They go down they go vertically up and down. So the notion that we could have a vessel, there's no robot or no submarine that exists that could launch, say at the Shannon or West Clare, follow close to the seabed and come up in the US of A or in Canada. It's just that it doesn't exist. So most of the ocean is actually still inaccessible. Robots can be designed to target certain zones. So we're working in this space. The oceans are unknown to us. Next up.
Yeah.
So the marine challenges. When we want to start unlocking this underwater world, the space guys, they have to develop their robot to survive takeoff. But once they're up there, they've only a 1 atmosphere difference between inside the rocket or the spaceship and outside. We have the same atmospheric or the same pressure for every 10 meters we go down. So 1 ton per fingernail when you're down at the Titanic. So pressure depth is a challenge. We've no radio communication. We can't navigate with GPS. We've turbidity, the water. I think there's an image up there of a pint of Guinness. I like putting pints of Guinness because I'm fond of it. But what we're really showing is what's beside it is a glass of turbid water. So some of the testing we do is, for example, in Limerick docks. We've also tested in Cork Harbour. When you take a pot of the water, it looks close to Guinness. So it becomes a barrier for camera work, for vision work, for lighting, and seeing what you're potentially going to bump into. So we use a combination of cameras, vision, LiDAR, lasers, and sonar. So there's so many challenges there. I'm not going to go down through the list, but maybe if you're quick reading, scanning readers, you might have caught some of them. There's lots for us to do if we want to enable and unlock that underwater world. And that's effectively what we've been focusing on in our research group. Dealing with the challenges so we can get the robots operating in these zones. Next up.
Okay.
So our team is currently of the order of 20, 25 people. Over time people leave and come, so I'm not going to list all the names because I'll leave somebody out and I'll include somebody who's left already. But not everybody who's left is considered our alumni, and some of you are here. So my co-directors, this achievement isn't my achievement. This achievement is all these people that have worked in the group and they've been supervised by me and my colleagues. So co-directors are Adair Dooley and Dino, who are both here, and Aoife is our coordinator. And I won't go naming everybody else, but because as I said, I'll leave somebody else out. Next up. So some of the robots. Most of these we built, some of them we purchased, but the ones we purchased, we then add our advanced control systems on. So we started with this little yellow sub, which was a little model of a manned submersible, built that way back started before 2000 and used it in experimental work in swimming pools and the like in the very early noughties. Tetra was an open-framed AUV we built. Ken Harris is here, and Ken and Paddy O'Donnell used to do an awful lot of our mechanical work in the workshop to support our building some of these robots. And the great interaction we had with them is we could design very actively by walking up and down with them. Because we were designing one-off vehicles, we didn't go to the full extent of doing full detailed engineering drawings, which you would do typically in any other engineering sector because it's not a one-off. So we've underwater robots that go to 1,000 meters, 3,000 meters. We've airborne, or that's on the next slide, robot manipulators. So maybe we'll go on to the next slide.
Yeah.
So on here we've some of the airborne systems. So blimps used to test radio communications, etc., in the marine environment. UAVs, unmanned aerial vehicles, multicopters, a large CGT UAV, which it's a bought-in system, but we've two airframes, and we're Jer and the fellas on the UAV side are developing lots of UAV technology that will land on this. So I won't tell you much about that because it's supposed to be my, you're not. But there's a whole wealth of research going on beyond what I'll cover in this short presentation. Next up.
Yeah.
So a number of the PhDs, the count's gone up to 22. Kevin said 21, and I've listed them in groups here. So I'm not going to go through every one, but we bunched them. So some of them are in the area of electrical engineering, developing electrical engineering technology so that to make the installations more robust, both electrically, so that to deal with the very harsh environment offshore, but also then the operations in the offshore environment, the humidity, the waves, the moisture, sealing against the weather, and then also integrating into the grid. Most wind turbines are grid connectable directly, which means everyone will you can control it to give you exactly 50 hertz, so it'll match to the grid. What we're saying is, let's do what we have a patent in this. Let's interconnect all the offshore wind farms together. Let them interact together in unison, but let them be frequency wild. Let them not be compliant with grid codes, because we can remove all the power converters from the offshore installation, one of the highest failure rate components, especially in high humidity and salt environments. We bring that power conversion to the onshore, and we convert to grid compliant 50 hertz voltage regulated power at landfall. So that's, for example, one of the patents. The other patents are in the sonar technology area. The next bunch is a bunch of PhDs in that submarine robotics, developing vehicles, developing the control systems, developing sensors so that it can work very close to targets. If you're operating in an environment where the turbidity is Guinness-like, it means you can't see the target you're about to bump into. If there's a wave or a current pushing you, we have to deal with how do we detect objects close to, when we want to work close to them, we want to maybe intervene on the targets, but we don't want to crash into them all the time. So maybe
Next slide.
there's some more PhDs, I think, in the next bunch.
Yeah.
There's area of sonar and sensors development. There's a best paper on the sensor. Sean Nolan is in the team here, so we've developed a sensor which got best journal paper over a 2-year period for the Journal of Marine Engineering and Science. Then we describe some of the offshore environment is very hazardous. So if we can remove humans from that offshore environment, let alone going down in submersibles, or even on the surface vessels, if we can bring them ashore and get radio communications to the surface and controlling the robot below. So a lot of what the research involves, how do we control things remotely from using radio? So that's in the marine environment, but it's in the air.
Keep going. This is more PhDs.
And then there's a few more PhDs there in airborne systems. And look, I think enough on those. I would better gallop on.
Okay.
So projects, we've listed some of the areas we've got funded projects in here. So we've an aero sub project, we've a Trident project. Trident is working on developing robots for monitoring deep sea mining. So deep sea mining is something that may happen over the next 10, 20 years. People have developed the machine capability, but back to our logo, we're interested in technology that if we do engineering and enterprise, we want to do it so that we improve the world, not open cast mining and affect the consequences. So the EU have funded a project which is trying to develop the monitoring capability, and they're hoping that there'll be international agreements because most of the deep sea mining will be in the open ocean. It won't be in territorial waters. So if there's international agreements, a bit like the protection of the Antarctic, and if there's the capability to monitor what the miners are doing. So if they eventually go mining for their nodules of manganese off the seabed, or mining close to the thermal vents, this project is aiming at developing the capability of monitoring what's going on, monitoring the plumes, monitoring the disturbance, monitoring the sound, etc. We're developing the robot capability that works right beside the mining machine in the most hazardous zone. And so we're using an ROV, which is tethered to the mining, sending all this information real time in live to the surface vessel, which is connected to the mining machine for the ore, so that we can monitor what's going on right there at the crunch point. And we won that it's a 14 million project with 20 partners, but we won it against a much stronger consortium. And part of our belief is that we had a convincing way of getting robots to operate close to a machine that's actually dredging up tons of ore per half hour, right there monitoring what it's doing. Anyway, that's just one project. And there's another one which is monitoring resurgam. If a ship gets damaged at sea, crashes into a submerged but yet floating container, damaged at sea, that project was aimed at, can we survey the ship to see the state of the damage? If the hull is bent in, rather than bringing it to a dry dock, can we design a repair patch and use friction stir welding to actually repair the ship at sea? So we're doing the robotics to survey the shape of the damage, go back to the naval architects, the ship owners, to design the patch, the specialists in the subsea welding, and then with the separate robot, can we offer up a patch and weld it to the hull? That saves getting ships that might get damaged, say, somewhere off, Florida, and it has to travel halfway up the east coast of the US to find a dry dock. Anyway, I've gone too slow if I give this much detail on every project. So there's many, many different projects. Next up.
Okay.
So this cold water coral project, this was one of our first projects that got us going. It was in collaboration with NUI Galway. It was funded under PRTLI, so the Programme of Research in the Third Level Institution. Marine Science Research, the lead was the scientists in NUI Galway, geophysicists and marine biologists. The interest was to map and discover the detail of some of these cold water coral mounds that had been discovered off the west coast at the edge of the continental shelf. If you image with a sonar on the ship, you'll get a very, next slide actually, you'll get a very low resolution image where you basically see the shape of the seabed, but you won't see anything smaller than the truck. So you won't be able to identify that's potentially a coral mound. If you see a slope, you won't know it's a slope, just a natural rock slope, or is it a very complicated geometry slope, such as a coral mound. So deploying ROVs, you can get this much, much higher map, geometry, topography of the seabed, plus video of the, so I think I'll be video in here.
Yeah, this is the automation.
I've the wrong version. I don't have the video in this one. Anyway, we'll skip ahead because
Would you do a short tutorial of the automation?
Yeah, no, I thought there was a video of the coral mounds down there, but we've loaded the wrong presentation. Sorry, it's almost the same thing. It's slightly different. So, as a lot of this audience aren't marine engineering technologists, I'm going to give you a short tutorial on how sonar works. So, next slide.
You do this, please.
So there's two types of sonar typically used. One is side scan, one is multi-beam. The side scan gives you more what they call grayscale detail, so that you can see like a very high resolution black and white image of the seabed. The multi-beam gives you the geometry of the seabed, so you know the X, Y, Z coordinates. So next slide.
Okay.
Is this, which one is this? Is this
Side scan.
The side scan. So the side scan, with the design of the transducers, you can form a sonar beam, a bit like if you have a torch. We have what we call the frustrum, which is the shape of the beam that's coming from the torch. It's generally conical, and the further away from it you are, the bigger the area it's illuminated. With the sonar, we can shape the sound frustrum to be, rather than conical, to be a fan beam. So it's only 1 degree thick in one direction, and it could be up to 120 degrees wide. So it's like a fan that's 120 degrees wide by 1 degree. We point that to the seabed, send off a ping, that ping goes to the seabed and echoes. So we're getting a narrow strip of the seabed ensonified on a vessel. So as the vessel progresses, we ping again, get another narrow strip, ping again, get another narrow strip. So we build up this waterfall image of the seabed. So I'll go to the next slide.
Okay.
So this one I'll step through and show you one of the transducers sending a ping towards the seabed. This animation was one of the PhD students a long time ago. He may be online, James Reardon. So thanks, James, for your slide. I've been using it for a long time. So we see the sound coming down towards the seabed. As soon as it touches the seabed, the reflected energy intensity goes back up. So we're plotting the energy intensity below. It starts to go back up, and whenever there's a rock, as the sound energy is coming down, or something standing up proud of the seabed, you get a stronger reflection. And behind the rock, you get a shadow where you're getting a weak reflection. So you get this graded, bright, dark representation of what you're looking at on the seabed, and it's actually human interpretable. So that's what we're. So there's 9 steps in that, and then we putting little narrow line after narrow line after narrow line in what we call a waterfall display. We end up with what looks like a black and white, or they make the different colours gold and less gold, in order to sell their sonars images of the seabed. We're now onto multi-beam. Multi-beam is trying to do a different thing. We're trying to measure the actual range, how long it takes to get the sonar energy to the floor and back again. If we know the velocity of sound, we can tell the range. So if we control the pointing angle and the time delay, we can map a whole lot of points on the seabed. So we do that by sorry.
No.
Which, so I skipped on this slide. We do that by having a projected beam, fan beam shape, but then a listening beam, which is also fan beam. But the listening beam is, and by listening beam, it we just have the same transducer, but mounted at 90, similar transducer mounted at 90 degrees. But because it's a phased array, we can steer the angle which it's listening at. So we can interrogate the projected array narrow fan beam to get 120 or 240 range angle pairs across the beam. So that's the end of the tutorial, and now we'll go back to the, are we on the next slide?
Yeah, we're on the research cruise CE0505.
Okay, back to survey. So we did a survey cruise with the folks in NUI Galway, investigating the coral mounds on the edge of the Atlantic aboard the Celtic Explorer. We were the engineers. We were integrating the inertial navigation systems, the sonars, all the techie stuff, and the scientists were the geophysicists and the marine biologists interested in the corals and the species and the size of the mound and whether it was rock beneath the coral or is the coral thousands of years old, coral on top of coral on top of coral, that sort of detail. So we're the techie people that were helping them do that. So next up, one thing we did on this survey, it was we were integrating the expensive instruments for navigation and imaging onto a leafed ROV. Again, with Sean Nolan, some of the team here, whatever offshore, Dino, etc., who were way back in 2005, I think it was. we thought there's nothing in that ROV we couldn't build ourselves. So that's exactly what we did. We is that imaging that that's when we decided we're going to go build Lattice. So we built our own ROV, which is 1,000 metre depth rated, and that's in there. So, and then we use that without having to hire in expensive ROVs from Norway in the following. So we'll go on next.
Okay.
So the next, I'll give you a little quick of the science results. The coral mounds and the different species of corals found on some of these coral mounds. The scientists among you might know of or be interested in the species and the differences between the different corals, but also the very interesting thing about corals is the range of fish and nurseries for fish species that they offer. So they're very important in the ecological sense. And the fact that we've discovered there are coral mounds way down in the deep dark ocean, not only in the barrier reef type corals. Next.
Okay.
So this just gives you an idea. The grid there represents the gridding that's done after the Irish National Seabed Service. So in Ireland we've mapped nearly all the territory, our seabed territory, which is 10 times our land base. You do that in the deep water with ship-mounted sonar and then grid it so that you know the shape of the seabed. So we know it's how far out the porcupine bank extends, where the slope falls off, where the porcupine sea bite is, all the features between the porcupine and rockall. So all that information is known from seabed mapping, but if you want to know the geometry and which is coral mounds or which are rocks or which are wrecks or which are whatever, we need to go in for a close look with higher resolution sonar. So we go in with ROVs because the long range sonars that will penetrate long distance, they work at low frequencies and we can only grid to relatively low resolution. What we've done here, or again, the scientists in Galway generated this image and draped the high resolution image over the low resolution bathymetry. So you can do much more science at the much higher resolution. So we go on to next.
Okay.
Okay, so what about? So survey above coral mounds are the coral mound. It's effectively formed by living fauna, but it's effectively almost like a rock. It's solid, so it's not moving. While there might be currents, if you were in the shallow waters, there might be waves crashing that might disturb the imaging platform, but the target is stationary. So some of the challenges, if we want to do high resolution imaging in other zones, if we want to support offshore wind energy, if we want to survey for erosion on the cliffs, we're going to be working in much more dynamic areas where there's currents, there's waves, there's disturbance. So effectively what we're interested in doing is doing more and more challenging work in robotics, in more and more challenging, meaning intervention coming close to targets, but in higher and higher sea states and in stronger and stronger currents. So for example, if we want to maintain offshore wind, if we have to wait for the one calm day a year, I'd say it's quite calm out in the Atlantic today. Lovely day for going out getting sunburned while you're deploying your ROV. But if you want to be able to service and survey an offshore wind farm 120 or 200 days a year, you'll have to be able to operate in up to sea state 4, 5, 6. And that's challenging. So if you're trying to bring imaging robots close to a target, if the target is stationary, the robot is getting disturbed by the conditions, or if the target is floating, if we've got offshore wind farms and floating wind turbines, floating target, floating service robot, everything's moving. So we're into a much more dynamic situation. So that's in effect some of the areas we're working in. We'll go on to next.
Oh. Yeah.
So what I've done in that tutorial is tried my best to. So what I'm going to do for the next 3 bits, I had a little twist that I've forgotten about, so I'll do that now. I was thinking, how would I do well, actually, without being able to see the slides. So one way of doing it is I can show videos. So that's what we're going to do for the rest, for the other project example. So will we launch this one right click or?
Now click again.
So this is a video of the robot work we're doing in supporting offshore wind. So I'll let the video do the talking and I can talk in general over it. I hope I'm not completely out of sync, but effectively when you want to put offshore wind out there, we have to do ground truth. We have to check the state of the environment before we do anything so that we can monitor whether we're adversely affecting that environment. We have to map the seabed, we have to find the geology, the rocks, the sand, the sediment. We have to plan the routes of cables, we have to plan the foundations, we have to get the other engineers to build their towers, the wind turbines, the nacelles, all that electrical stuff, all that mooring, and then we also need to be able to maintain and service all this equipment through its operational life and eventually re-wind it when we need to replace some of the components or decommission it and take it out. So we need robots at nearly every stage in that. So in this, is the video running?
Yeah.
So in this video, we're showing we're active in doing some work on, there's a floating offshore wind farm in Portugal. We've done underwater imaging of the floats. So part of the engineering work you'd want to do is monitor your flexible risers, your mooring chains, your floats for corrosion, for growths, so you might have to clean them underwater to take the algae and the growth off so that you can inspect for rust, we put protective anodes on the structure so that the anodes dissolve in the ocean rather than steel dissolving in the ocean. So there's a lot of work that needs regular inspection and maintenance. And we want to do as much of that as possible, or all of that, with robots in the water, not divers. So a bit like the oil and gas industry, once they went into deeper waters, they took all the divers that they used to use in the early stages of oil and gas out of the water and they replaced it with robots. The offshore oil and gas is in deep waters where it's generally dark but quiescent. You don't have breaking waves, you don't have very strong currents. You have currents but not very strong. In offshore wind, we're going in zones with high winds. We wouldn't put them there in the first place. High winds is high waves. So a combination of currents, winds, wave, it's a very challenging place to operate with the robot. So effectively that's where we're up to. So that's more or less, I think we've come to the end of that video.
It's still going. Do you want to go to the end? Yeah.
Yeah.
It's nearly done.
So when I had better vision, I'd talk to the video as I could see it, but
it's done now. We go to the next.
Oh, we're finished, so we can go to the next.
Now.
So the next area we're going to show that we've been working on is, which one is this?
I'll play it now. It's played.
So this is the shipwrecks.
Yeah.
Again, if I didn't include it, I forgot to include it. There's a map that Marine Institute have done of showing the scatter of all the known shipwrecks around Ireland. If you put a dot for each map around the coast, you end up with, on their map it's a red dot, you end up with this, what looks like flower petals scattered under a Japanese maple tree at this time of year, just literally covered with red dots. The northern approaches during both World Wars, the U-boats used to sit in ambush waiting for the transport vessels, so there's a huge tonnage of shipwrecks going around Donegal trying to get into Glasgow and Liverpool, and then off the south coast trying to get into the Irish Sea. So we did a survey. One of the surveys included UC-42, which is a U-boat just off Roach's Point. They discovered there was this bump in the bathymetry close to 150 metres from the gas Kinsale pipeline. On closer investigation, that turned out to be a U-boat. And when we did the survey off the Ellie Etna with our robots, it turned out there's still TNT mines on that, or that submersible. So a lot of the imagery up there shows the video from the actual mission, some of the sonar image, generating the sonar in real time, generating a sonar model showing the shape of the submarine robot, and then the other vessels, there's an image of the mapping of the Empress of Britain, 1 metre shorter than the Titanic. It was sunk 50 miles off bloody foreland, again close to the end of the Second War. And there's other wrecks up around Donegal on there. So if you investigate, like if the wrecks are more recent, there might be a salvage component to it. If it's in very close after a disaster, you may have some amount of recovery involved. But again, you need robotics to access this type of capability. Next up, I think our last example.
It's still going. Do you want to keep?
Oh, it's still going, is it? Okay.
Yeah.
So sometimes the video you see on the seabed, because of the high turbidity and the fact the further down you go in the ocean, the less colour you get, because the colourful wavelengths get absorbed in the shallower waters. When you get down deeper, any of you who are into scuba diving will know the deeper you go, the less colourful it gets. And anybody into technical diving, as Gerard Dooley, our co-director, does technical diving down to 150 metres, you get to the point where there's not much colour, but there's lots of shipwrecks. So in fact, there's a lot of enthusiasts who go after shipwrecks.
Still going.
Still going. Oh, maybe we'll.
Will we continue?
Yeah, I'd say.
Okay. 1 second. Now the last video.
The last video then is, it's very prevalent in the news recently, the threat to our submarine assets, cables, pipelines, etc. If the gas pipeline interconnections between Ireland and Scotland were disrupted, 38% of our electricity generated by gas. We don't have a lot of gas storage, so if those gas feeds were interrupted, we'd have electric power shut down within a couple of days. So there's obviously very high risks with those, with the power interconnectors to Britain and the new power interconnector they're putting out to France, and protecting the cables going out to the offshore wind farms as they're put out. And then the fibre optic cables, the data cables, the same issue. So we have the survey capability to monitor, map, check that there's nothing untoward happening on the submarine cable. So in fact, this video shows some of our work down on the Kinsale gas pipeline. Kinsale is now past end of life. They've capped the well. Where they took away the Christmas tree and they've just the capped off pipe coming up. We were checking for leaks or small bubbles. We passed by it, but what looks like a photograph of our ROV sitting over the pipe to check are there bubbles coming up, and there was bubbles coming up, but they're at once every 10 minutes, or a very, very low seepage rate. But it looks like a photograph because it's not moving, and that's because our control system is so good. The control system is able to hold our robot absolutely still in the ocean. And then also included in that video was high resolution imaging of pipelines and the mattresses. So in engineering, we can check the structure, we can check if there's any mechanical risks that need servicing, or is there any threats such as, etc. So that's, have we come to the end of that one?
Come to the end, yeah. I'll go to the next. Oh, it's playing again. Let me go to the next.
And then we're on to the last one.
Oh, sorry, you want to go back to a different video? I think it's the same video twice.
Oh, is it? Okay, sorry.
So we'll go on to the develop lab and operation.
Okay, so we've had many projects. We've had a large amount of funding from European projects, large amount of funding in Science Foundation, Marine Institute, SEAI and other agencies. Our test facilities include a 2 by 3 metre tank. So one thing we have to do is get everything right first time when we build the robot systems to go offshore in the ocean, because the cost of a surface vessel such as the Celtic Explorer is 18,000 per day. So we don't want to get on the back of a 18,000 per day ship and find we've forgotten a fuse, because we're wasting 18 grand while we wait for somebody to bring out the fuse. So a huge effort we do is getting all our engineering and development work working first time through simulation, integration, building, testing as best we can in a 2 by 3 metre tank. And to some extent, that's a testament to the very hard work of the team. But what we're interested in is now trying to convince the government agencies and the UL to support us in this too. There's a need for this capability. We're the only research lab in Ireland that's active in this field, robotics. What I haven't covered in any detail really is all the airborne side of what we do, which there's as much and more again. But we're interested in convincing people Ireland needs the capability. So I think it's on the next slide actually. It needs the capability to go for a national lab in this area. So we're pitching and trying to convince people that while we've had great success, I'll be retiring soon. That's one thing I never said. Inaugural lecture, I actually became professor back in 2018. So I ducked under the wire for a number of years, and they didn't know that they let me away without doing one. So I'm doing one unusually in less than a year before I retire. But so be it. It's as good now as any other time. So so I think that's where we are.
We go to questions?
Yeah, so any questions? And what I meant to do was sit down here, pretend I was Dave Allen, and drink a whiskey.
I've seen a lot of Dan's presentations over the years, and he has some fantastic videos. I think you've only seen a fraction of what he actually has recorded under the oceans over the years. So does anyone have any questions? Yeah, Martin.
Hi Dan, I know you probably won't see me, but I'm telling the referees anyway that people can recognise my voice. So I suppose, a comment on the question, I suppose we've soldiered together for a long time, back to the old AMT days. And I always remember, for example, the sign beside your desk, don't get phased by TLAs, right? 3-letter acronyms. And it just actually spoke to your healthy distrust of kind of buzzwords and strong focus on fundamental core disciplines. And I think that's a hallmark of your career. And I think a question, having, borne witness to your strong advocacy for your group and your discipline over the years, if you were to recommend to government, right, what's the best way to spend the significant sums that they have available to them in order that Ireland Inc. would get best bang for buck in terms of investment in its kind of natural resources, specifically looking at kind of how best we can leverage the benefits of our wonderful estuary. How would you recommend, what would you advocate for?
Okay, with that question we could stray into the political side, which I guess isn't my forte, but we certainly have public discussions over the political side. So to some extent what Ireland ends up doing is sort of procrastinating. I thought 20 odd years ago when we got involved in this space that the offshore wind was around the corner in Ireland. We were the first in Europe to put turbines in off Arklow, and we've done nothing since. And we have been promising to do the whole 9 yards, and we've promised 6 gigawatts. But the rate at which we're doing it and the legislation and regulation side of everything involved, it's a bit like the housing. The bureaucracy is getting in the way. If we could somehow get back to what Ireland did as a new state, it managed to do Ireland and Crusher within the first 10 years of its existence with practically no money. So I don't know how they did that economically, but they did manage to do it, and they electrified the whole country. So that's sort of, it's a technical, political statement. I've been an advocate for renewable energy and offshore wind for a long, long time, so I think we just need to get busy and get on with it. It's really what I'd say. And we need to do a lot of all this technology development in order to make it happen.
Any more questions?
I was just going to ask, does the university earn any money from the projects and the work you've done there?
No, not directly. And so obviously some of the income from research funding must go to the university that we're housed here, the lights, all of that 9 yards. So there's overhead, some of which goes directly to the university so we can be based here, some of which goes back to the group because we've hidden costs that we must cover as well. But also then we've a couple of patents. The idea in this technology area, somebody finished a PhD, does postgraduate research, they could take out, and the research is funded with the notion that they can take out some of the intellectual property through startups and start businesses and start high-tech businesses. So there are numbers of opportunities for that in this technical area, and many of the funding agencies ask me, why aren't we doing more of that? And the reality, the real reason I didn't do that is the same reason I never became head of the department. If I took on such a role, I would have crashed this activity. So in order to build this research capability, it's absolutely rich pickings for some of the researchers, and some of them are in industry, and some of them have tried startup companies. Startup companies have a high failure rate, but then some of them obviously burst through escape velocity and off they go. So that's the feedback really. So the government isn't taking a 50% slice, but it's taking enough money to help us do what we do through overheads. And the real payback through state funding is supposed to be through the enterprise economy that it grows?
Well, yes and no.
I thought you said it's no politics.
Joe Gibbs there.
Hi Dan, it's Joe Gibbs. I guess we've known each other about 10 years, but every time I see a presentation from you, or I see a video, or we talk about some of the work that you guys have done, I've always been amazed by how I guess that it's applied, but it's impactful and it's research, that it ticks all those boxes. But I guess when you look back professionally over your career, what would you like to be remembered for, or what would you think is maybe one of the biggest achievements that you've had?
Just hard work and commitment and dedication. So, you know, a lot of people don't get too distracted by the politics. We can all, as I say, take it in public, have a good argument about politics. And I don't mean just government politics, but also interpersonal politics in any organisation or in any group. But I mean, to some extent, of course, and to believe in yourself, even if nobody else sort of gets it. But to some extent, one thing I criticize all universities for is this notion that they put so much effort into strategy. The strategy is get out of the way, research and writing is the strategy. The strategy isn't take it up to executive writing strategy that makes no hard. Never has this area that I've been working into US strategy. Yes, it's one of the biggest groups in the US, been happening for 20 years. So, you know, that strategy piece isn't working. And I'm now in danger of saying materials. I shouldn't be HEA, one of the most important roles they want from the president is to update the institution strategy. I think one way to update the institution strategy is say get out of the way of researchers, and then to update it, all you do is take off up and ask them, blow the dust off, add a few words, put it back. That's strategy.
Can I make one comment on what you said? Because I think we'd be too humble to say it, but I think the reason that those kind of things happen is down to individuals like yourself who are passionate about making it happen, and therefore you bulldoze through those obstacles and you actually do the work, you do the research, you create risks, you create those various different things. And I think whatever about having a strategy, if you don't have individuals like that, with that passion, that, like you said, strategy is just something written on a piece of paper.
Yeah. I'm that first, actually. I think Dan is probably, he epitomises a lot of what our department are. He's a theorist that can actually turn into practical work. So I think that's quite unique in a lot of universities around the world. We tend to focus on the theory and simulation and forget about sometimes it has to go in the water. Any other, one last question?
Can I make a comment?
You can, of course.
Yeah, I'm Karen Wiltshire. I'm down for years on the House earlier and I'm the first chair of sciences. And I just wanted to say that from an international perspective, if you look at Ireland and engineering, and this always stood out. Also in the Helmholtz, and I don't know if you know what Helmholtz is, it's Germany's largest engineering and science institution, and with 80 huge institutes, including the Space Agency. And I spoke to the president of the Helmholtz the other day, and he knew what you were doing. And I just wanted to tell you that I was so proud that I knew you, and that I could say, I know him, and I know his group, and it's always been extremely good, and just out of and above the ordinary. So I sometimes think we Irish find our lives a little bit too much under the bottle. And if the Helmholtz organisation sees it, then I think it would take the life out. I mean, it's just trying to get it right, sell yourself a little bit more, and for all the companies and students, and that the university too, I may say so. So anyway, congratulations, and I'm delighted that I could be here today.
I think that serves as policy. To leave it there, Dan, do you want to do? Before Dan, while Dan is doing that, I'd like to thank Dan for his presentation. I'd like to thank Lily for running the show. That's the first time Dan's ever finished on time.
So what I'm going to do, which is a bit odd, is no, actually, two colleagues I think did introduce into their speech some music. One was Thomas Party, and the other was Luke Federer. I'm making up. They were two I attended. So
Actually, I'm not singing.
So it's a bit of an honor. I will play a tune, and it's called Just the Whole Trip to Milltown, or subtitled The Romance from the Gadfly Gone Away. So you'll recognise it, or part of it at least. And my understanding, if I'm close enough to the microphone, actually I've got a microphone on myself, it can be heard. So I'm sweating and I might get nervous and put a whole lot of bum notes in this. We'll try. In fact, those contact glasses, while my vision is poor, that makes it even worse. No, I've lost notes. Sorry.
Thank you all for coming down to our lecture.
Thank you.